Good evening and welcome back to AP Stats Notes Online. We talked last night about the sampling distribution of sample means when we were sampling from a normal population distribution. So some population that is deemed to be approximately normal, and we discovered that the shape of the sampling distribution of sample means was approximately normal as well. So, but we didn't talk about what happens when the population distribution is not normal. And remember, we're talking about population distribution, the shape of a population distribution now, and we weren't talking about it when we were talking about sample proportions, because the sampling distribution of sample proportions is coming from a population of a categorical, of measuring a categorical variable, and therefore the distribution is a bar graph, and it doesn't have a shape, center, or spread. So it didn't make sense then, but it does make sense now in talking about sampling sample means. So let's do that. Let's take a look, and we'll go back to this Rice University applet and take a look at some population distribution that is very skewed right. Some things that we need to understand about this population distribution is that the mean is 8.9. The median is 7, so the fact that the mean is higher than the median lets us know that it's very skewed right or skewed right. And the standard deviation is 7.8, okay? So let's take a look. What happens when we start sampling? So if I pull a bunch of numbers from this population distribution that is skewed right, I can do it once. I'm still going to pull 5 numbers and drop that mean down, and I'm going to start this over. Hang on just a second. I don't want to do this one just yet. So I'm still going to pull 5 numbers, calculate the mean of those 5 numbers, and drop that mean down into my sampling distribution. Now I'm sampling 5 at a time, so 5 numbers at a time. And so far that is 1 sample. Now I want a better idea of what's going on with my sampling distribution, so I'm going to do it another 1,000 times. When I do, there's the sampling distribution. You can see down here that the mean and median are not quite the same, but they're pretty close. They're definitely closer than they were in for the population. So what does that mean? I mean, we are getting closer to symmetric. We are getting closer to what we hope to be a normal distribution. If we try to fit a normal curve to this guy, it's not a great fit. You can still see a little bit of a right tail on this guy. I don't know that I would go so far as to call it right skewed, but it's definitely headed that way. Now, that's if the sample size is 5, and we can pull as many samples as we want. As a matter of fact, I just pulled another 10,000, and the mean and the median aren't exactly the same, and we have added some results over here, so we're getting a little bit more of that right tail. Okay. So the sampling distribution is not going to automatically be normal if we're sampling from a non-normal population. Well, that's not good for us. We want a normal sampling distribution so that we can do some probability calculations a lot easier. Okay? We could take a look at the fact that the mean is still pretty close to the population mean. The standard deviation is 3.52. If we were to take 7.8 and divide it by the square root of 5, my guess is we would get a result pretty close to 3.52. As a matter of fact, we can check that just so that I'm not talking about things that may not be true. And it is. You get 3.49, so pretty close to the 3.52. So, the mean and the standard deviation are still behaving the way that they should. It's just the shape that is not what we want it to be. So the question becomes, does the shape ever become normal? And we can always do a sample size of 2. If we do 10,000 samples of size 2, then here's what that sampling distribution would look like. Okay, it's even less normal than the other sampling distribution. And so the shape of the population distribution does matter. Okay, again, we never talked about it with proportions, and we've already talked about why. Now the question is, does it ever get to be approximately normal? What if we took a sample of size 25? Okay, and I'll compare the two. Sample size 2, sample size 25. I'll pull 10,000 samples for each. And take a look. In the sample size 2, this sampling distribution is still definitely skewed right. You can see that the mean and the median are not very close together. And when our sample size was 25, it's a lot closer to normal. Our mean and median are a lot closer together, and our normal curve fits it a little bit better. So while the number of samples doesn't get us any closer to normality, apparently the sample size does. And this is something called the central limit theorem. Okay? And so as a matter of fact, as our sample size increases, our sampling distribution will get closer and closer and closer to normal, to a point where we will feel comfortable saying that a sampling distribution is approximately normal when our sample size is a certain size. Okay? So let's use this discovery to answer some of the questions in our notes. What is the shape of the sampling distribution of a sample mean when the sample is taken from a population that is not normally distributed? Well, what we just discovered is the shape of the sampling distribution takes on the shape of the population distribution. Let's see, distribution takes the same shape as the population distribution. Hello. All right. Of the population distribution. Okay? And this is for small sample sizes, smaller sample sizes. Now the next question is, does sample size matter? Yes, it does. And we saw that it does, yes. And what we notice is that as long as the sample size increases, the sampling distribution becomes more normal. Okay? Now, okay, this gets us to, again, what I mentioned before, which was something called the central limit theorem. And if you can find some extra space somewhere, I want to bring that down here. Okay, the central limit theorem states, it takes this idea of sample size matters and puts a number to it, right? Central limit theorem says that when sampling from a non-normal population, the sampling distribution will be approximately normal when the sample size is greater than or equal to, and 30 is that number that we put on there. Now, we go back to the applet, and the largest sample size we could take was 25, and 25 was getting pretty close, right? 25 was getting us pretty close. And so 30 has become sort of this universally accepted, or at least in AP statistics, accepted as the sample size that gets us to approximately normal. So when is the sampling distribution normal? The sampling distribution, well, never, right? The sampling distribution is approximately normal when? Well, when the population is normal or approximately normal. Okay? Or when n is greater than or equal to 30. So that's when we can tell when the sampling distribution of sample means is approximately normal. And remember, with sample proportions, as long as n times p and n times 1 minus p were both bigger than or equal to 10, then our sampling distribution can be considered approximately normal. Okay? And we want to apply this central limit theorem whenever we need to. And so it allows us to perform our calculations even in a situation of a non-normal population. So this example here, suppose the number of texts sent during a typical day by a randomly selected high school student follows a right skewed distribution with a mean of 15 and a standard deviation of 35. It's probably not surprising that the number of texts sent during a typical day would be right skewed. You would have fewer people sending a ton of texts, and the bulk of students sending not, I wouldn't say few texts, but sort of clumped together. So it would make sense that it would be something like this. Assuming that students at your school are typical texters, how likely is it that a random sample of 50 students will have sent more than an average of 20 texts in the last 24 hours? So how likely is that? Well, let's get into it, and I'll do this one in terms of a 4-step process, right? So state, what question are we going to answer? There we go, thank you. Right? And I'm going to reword it a little bit. What is the probability that that the mean number of texts sent for a random sample of 50 students will be more than 20. Okay, and that'll tell us how likely it is that a random sample of 50 students will produce a mean of 20 texts, right? So plan. Well, we want to get into our sampling distribution because that's what's going to tell us how likely it is to get a sample of 50 students that have a mean number of texts sent of 20, of more than 20. So I want to produce the sampling distribution to have an idea of where a sample would fall when they had a mean number of texts of more than 20. So I want to check to see if the distribution is going to be approximately normal. When we're sampling 50, which is definitely more than 30, So this is going to be approximately normal. The mean, what's the mean of our sampling distribution? Remember that sample means is an unbiased estimator. So our sampling distribution mean is going to be 15, because that's the mean of our population. And the standard deviation of our sampling distribution is going to be simply taking the standard deviation of the population and dividing it by the square root of 50, right? And so we do that. And we get 4.95. So since we've determined that our sampling distribution is approximately normal, having the mean and the standard deviation of that sampling distribution is going to be very, very useful. So approximately normal, mean of 15, standard deviation of 4.95. Now, we want to see how likely it is, what the probability of getting a mean whose sample is bigger than 20 is. So remember, this sampling distribution is supposed to give us an idea of how often samples would give us a certain mean if we're pulling from a population that is as described above. So I'm going to add 4.95 to 15 and get 19.95. Add 4.9 again and get 24.9, and that'll get us as far out as we need, because I want to be at 20 or more. Right, and now it becomes a normal calculation issue. Okay, so how do I find the probability? You can use normal CDF. So the probability that X bar is greater than 20. We can do normal CDF with a lower bound of 20, an upper bound of, 100 would be enough, with a mean of 15, standard deviation of 4.95. Or we can do our z-score calculation, which is going to be 20 minus 15 divided by 4.95. Get into table A, and remember that table A always gives us probability less than, so we're going to have to take that value from table A and subtract it from 1 to get more than. But either way, and I'm going to use the calculator because I think it's so much faster. Uh, 4.95, and I get approximately 15.6%. Okay. So we would conclude there is approximately a 15.6% chance of a sample of 50 students producing a mean number of texts that is more than 20. Okay, so the population suggests that the mean number of texts is 15. And so since a sample, we're talking about a sample producing a mean bigger than 20, does that suggest that the students at our school text more than the entire population does? Does it provide evidence that if we get a sample and the mean is 20 or more, that that sample does not come from the population described above, right? Well, there's about a 15.6% chance that from the population above, we would get a sample of 50 students whose mean number of texts was more than 20. And since 15.6% is not that unlikely, then we can assume that a sample that produces an average number of texts of 20 or more could very likely come from a population whose mean is 15 and standard deviation is 35. So we don't have any evidence, or we don't have any indication that our students at this school are any different textures than students in the entire, country or population. Okay, so our score is not different than anybody else. Okay? Anyway, central limit theorem is key here. As long as our sample size is bigger than 30, our sampling distribution will be approximately normal, and that'll set us on our path to do our probability calculations. Okay? That gets us through Chapter 7 and sampling distributions. Homework is in the text. You can start working on that either now or in class.